Jai Hind everyone. Welcome to the class of Optical Communication. This is Dr. Naresh Kumar from Akgec Engineering College, Ghaziabad. In this lecture of Optical Communication, we will discuss optical sources and mainly the focus will be on laser diodes. So the main contents for today's lecture are basically we will study the introduction about laser, basic working principle of laser and cavity based laser structure with optical feedback and laser oscillation and resonance. This is mainly to achieve the process of amplification. Then we will cover the laser modes, also known as the laser lines. Then finally we will discuss the threshold condition for laser oscillation, and then a numerical will be discussed related to this threshold condition. So first of all, what is laser? Laser is basically a source of light, and this source of light is generally used in the optical communication on the transmitter side. And we know that the laser is used in the optical transmitter, and the main purpose for using this laser is basically optical source is required for generating the carrier signal. The optical sources are also required for achieving the modulation, for example, intensity modulation. Moreover, basically it is used for electrical to optical conversion. So optical sources in the transmitter side are required for generating the carrier signal in the form of light, intensity modulation or electrical to optical conversion, so that the optically converted signal after modulation can be transmitted through the optical fiber cable. So the light sources can be LED, for example, LED or laser. Okay, so the LED can be used or laser can be used. We have studied the comparison in previous lectures. The laser is basically a monochromatic, coherent and a focused beam of light. As compared to LED, the laser is a monochromatic, coherent and a focused beam of light. Along with this, there are a number of advantages that we have by using the laser over the LED. That is, if we use the laser as a optical source in the optical communication system in comparison to LED, we get a number of advantages. For example, the spectral line width of laser is less. That's why we get the dispersion or intramodal or chromatic dispersion as low in the case of laser. So there are a number of advantages. Let's see. First advantage is high radiance due to the amplifying effect in the stimulated emission. Basically, the LED uses spontaneous emission, whereas the laser uses the stimulated emission. In the stimulated emission, we get a number of secondary photons keep on generating. So there is high radiance effect. Moreover, in the laser, what we have is light amplification. Light amplification. So basically, laser stands for light amplification by stimulated emission of radiation. So amplification of light is also achieved with the help of cavity based structure in the laser. So with the help of this stimulated emission as well as by using this amplifying effect in the laser, we get high radiance and the optical power generated by the laser is comparatively more or higher as compared to the LED. Another advantage is narrow line width of the source. So if we compare the spectral line width of LED and laser, the spectral line width of the laser is comparatively less. That's why we get the minimal effect of material dispersion. We know that the material dispersion or chromatic dispersion sigma m equal to sigma lambda L m, where this sigma m is known as the sigma lambda is known as the spectral line width of source. So we can see that the material dispersion is directly proportional to the spectral line width of the source. So in the case of laser, the spectral line width is less, so the material dispersion or chromatic dispersion effect is also less in the case of laser. Whereas in the case of LED, the sigma lambda is higher, so the material dispersion will also be higher. Another advantage that we get with the laser is modulation capabilities. The modulation capabilities for the case of laser is high as compared to the LED. Here the modulation range goes into the gigahertz. That is, a signal of frequency in the range of gigahertz can also be easily modulated with the help of laser using the light as a carrier signal. Another advantage is relative temporal coherence, which allow the heterodyne detection or coherent detection at high capacity system. So because of relative temporal coherence with the laser, we get advantage of using the coherent detection, or we can also say that the heterodyne detection. Generally with the LED, we use only the direct detection. That is, we use the principle of intensity modulation and direct detection in the case of LED, whereas in the case of laser, we can also use the coherent detection, and preferably the heterodyne detection can also be used. Another advantage is good spatial coherence, which allows the output to be focused by a lens, and as we have already studied, the light emitted by the laser is generally a coherent monochromatic and a focused beam of light, because the light gets emitted from the cavity of the laser with a particular point, because through the one of the mirror which is partially transparent. So here we get a focused beam of light. So what is the basic principle of using the laser? How light can be emitted in the case of laser? Basically, laser is electrical to optical conversion. So, and optical sources are forward biased. So when the optical source is forward biased, basically the electrons are injected and these gain energy and these go into the higher cell, and there is, whenever they come down, there is recombination of electron and hole pair. Electron and hole pair recombine together, and after recombination, energy is released in the form of photons or light. Energy equal to the band gap is released in the form of photons, or we can say that light is emitted. Basically, whenever the diode is forward biased, electrons are injected and electron hole pair recombine together, and the band gap is energy equal to in the band gap is released in the form of photons. So this recombination of electron and hole pair are recombined together. This recombination can be achieved either through this stimulated emission, and also amplification of light can also be achieved using a cavity based structure. So in this cavity based structure, we achieve the amplification of light and also the both spontaneous emission. Recombination can be through spontaneous as well as stimulated emission. However, in the case of laser, this stimulated emission is dominating one. So as discussed, the emission process can be because of spontaneous emission, where the electron and hole combine together and the electron in the higher state come to the lower state purely in a random manner. So in this case, the number of recombination are less and number of photons are also less. So the very less contribution of spontaneous emission is there in the case of laser. Now in the case of stimulated emission, we use external photons having energy equal to the band gap interact with the atom in the higher energy state or electron in the higher energy state. That is, the electron present in the higher energy state is forcefully brought down to the lower state so that the electron hole pair can recombine together, and this process generates another second photon. One photon is that we are using for incidenting, one photon is external photon having energy equal to the band gap, that is E2 minus E1, which is used for as incident photon to brought back the higher state electron into the lower state. Second photon is generated, this is by the recombination of electron and hole pair. So in this way, after another photon is generated, we get two photons. Now these two photons can be used for generating another two photons by colliding the atoms with each other and generating the another carriers. That is, secondary generation of carriers can take place. And this effect can also be known as the avalanche effect. Another important phenomena is, for achieving the stimulated emission, the process is known as the population inversion. Basically, what we are doing, we have a higher state and a lower state. The electron is present in the higher state. It is brought back down with the stimulated emission, and here the electron and hole pair combine together and energy equal to the band gap is released in the form of photon. These photons can be released only when we have density higher in the case of upper state. That means the particles present in the higher state or upper state should have higher density as compared to the lower density state. This process is known as the population inversion, and this can be achieved with the help of some external energy source, and this is known as the pumping. That means for the stimulated emission, we need to have more number of electrons in the excited state or higher state as compared to the lower state, so that we can brought back it down and electron hole pair can combine together to generate the photons. To maintain the higher density in the upper state, this is known as the population inversion, and this can be achieved with the help of external energy source, and the process is known as the pumping. So laser basically works with spontaneous emission, stimulated emission, and for achieving the stimulated emission, we use population inversion through the pumping process. This is the working principle shown in the form of diagram. So basically what we have, initially whenever we forward bias, then the atoms gain energy and it goes into the higher state. This process is known as the absorption. So after absorption, we have the particle in the higher state. Now this particle has to come down because this higher state is generally the unstable state. So this particle has to come down so that the electron and hole pair can combine together to generate the photons or light. Okay, so this electron from higher state to lower state cell can come down in two ways. First is purely in a random manner, and if it comes randomly at any time, this is known as a spontaneous emission. Another is to brought back this electron down to the lower state from this higher state. As the higher state is unstable state, we can use external particle. So we can use an external photon to brought back it down. So we are using external particle to brought back it down, and when it is brought back down, we have electron hole pair combined together and a photon is generated. But if this external incident photon has the same characteristics as this energy equal to this band gap, so both of these will have the same characteristics. So we have a monochromatic coherent and a focused beam of light, that is two photons are generated. This is known as the stimulated emission. Now these two photons can further be used for bringing down the another two atoms, so that another two pair of photons can be generated. So this process keep on going and a number of photons are generated or number of photons keep on multiplying. This is stimulated emission. Basically what happens, the laser characteristics will be like this. In the initial stage we will have spontaneous emission, where the number of photons will be comparatively less, but as soon as the threshold is crossed or stimulated emission starts, the number of photons increases, the light increases abruptly. So here we have the intensity or light output, and here we have the spontaneous, and here we have the stimulated emission. Okay, so here we have the current, that is forward bias current. Another is cavity based laser structure. Basically we know that in the case of laser there is amplification of light is there. Light amplification is there. To achieve the amplification of light, we use a cavity based laser structure, and this cavity based laser structure may be given a name known as Fabry-Perot cavity or Fabry-Perot resonator. Basically in this cavity based laser structure what we have is, we have mirrors on both sides of the cavity, then we have the length of the cavity is given there, and we have some kind of amplifying medium in between. This amplifying medium can be, for example, this can be a gas, for example helium neon gas. This can be, for example, a semiconductor material. Semiconductor material can also be there. This amplifying medium can be, for example, a crystal. So depending upon what material we are using as a amplifying medium, that will decide the type of the laser. For example, if this amplifying medium is a gas, so we will say that this is a gas laser. If this amplifying medium is a semiconductor material, so we will say that this is a semiconductor injection laser. And if this amplifying medium is a crystal, we will say that it is a ruby crystal based laser. So basically what happens, in this case the light is reflected multiple times from the two mirrors, and whenever light propagates in this fiber, what we get is this behave as a oscillator and a positive feedback is achieved due to multiple reflections from the both end of the mirrors. So due to this positive feedback or multiple reflection, what we get here is we get gain in the cavity. Okay, but the main purpose of this gain will be firstly to neutralize the losses occurring inside the optical cavity. So inside the cavity there are different type of losses. For example, transmission loss is there because of the length of the cavity alpha L. Both ends of the mirrors will not be perfectly reflecting, so there will be reflection losses. There will also be diffraction losses. Diffraction loss. There will also be scattering losses. Okay. However, these diffraction losses and scattering losses are generally negligible. So mainly inside the cavity there will be transmission loss and reflection losses. So the main purpose of gain inside the cavity firstly will be to balance out these two type of losses, transmission losses and reflection loss. And whenever the gain inside the cavity will be more than these two losses, then the light will come out of this cavity through this one of the partially transparent mirror. We are using two mirrors, both mirrors on both ends. So one of these two mirrors will be partially transparent. And when the gain inside the cavity balance out the losses inside the cavity, the light will come out through this one of the partially transparent mirror as a monochromatic, focused and a coherent beam of light. Inside the cavity basically what we have, there will be a condition of resonance also there. And as signal is reflecting from one side and another side, basically we have standing wave patterns are formed. Inside the cavity at the resonance we have standing wave patterns are formed, and these standing wave patterns are available at a distance or multiple gap of lambda by 2. Okay, at a multiple of lambda by 2 we have multiple standing wave patterns are formed. These multiple standing wave patterns available at a gap or interval of lambda by 2 or half of wavelength, these are basically known as laser modes. Laser modes, also known as laser lines. Okay, so at resonance condition we have the relation as L equal to lambda q by 2n. These are the parameters related to cavity, where this L is the length of the cavity, Q is the number of modes, lambda is the wavelength, n is the refractive index of the amplifying medium, for example crystal, etc. And where this lambda can be written as lambda equal to C by F. So we can simply, putting this lambda equal to C by F, we can compute F equal to QC by 2NL, where this frequency is for Q number of modes. So the separation per mode, separation between the modes can be obtained as delta F equal to, this is for Q number of modes, so divide by Q, we will have C by 2NL. So the modes, for example longitudinal modes in the laser, will be separated by a gap of C by 2NL. This is the gap. Separation between the modes is given by delta F equal to C by 2NL. These are the examples of modes occurring inside the laser cavity. So inside the laser cavity generally two type of mode occur. One type of mode is known as the longitudinal modes. These are the longitudinal modes shown here. These are the multiple modes. We know that Q number of mode exist in it, and separation between the modes or gap between the modes is given by C by 2nl. Second type of modes that occur inside the cavity, inside the laser cavity are transverse modes, examples of transverse modes are transverse electromagnetic 00, transverse electromagnetic 10 and 11. These subscript 00, 10 and 11, these basically define this direction of this alignment of field component or mode. So different direction are given there. One numerical example is there over this topic. So we have a crystal ruby laser, that means we are using amplifying medium as a crystal, where we have length of the cavity as L equal to 4 centimeter, refractive index as N equal to 1.78, peak emission wavelength lambda equal to 0.55 micrometer. Then what we have to get is number of longitudinal modes. Number of longitudinal modes are given as Q 2nl by lambda. All parameters are given, so we can calculate Q. Then basically we have to calculate separation between the modes, so it is delta F C by 2nl that we have previously seen, so it is 2.1 gigahertz. Next is threshold condition for laser oscillation, that we have studied. The main purpose of gain inside the cavity will be firstly to neutralize the losses occurring inside the cavity. So the value of the gain that balances out the losses occurring inside the cavity, for example transmission loss and reflection loss. This minimum value of gain to neutralize the losses is known as the threshold gain, or the condition is known as the threshold condition for sustained laser oscillation. So all the losses occurring inside the cavity are shown through this fractional loss, and all the gain occurring inside the cavity are denoted by the fractional gain. So all the fractional loss must be equal to or balanced out by the fractional gain. So we'll have fractional gain multiplied by the fractional loss is equal to 1. So in this case the value of gain that we are achieving is known as the threshold gain, and the condition is known as the threshold condition for laser oscillation. That is, inside the cavity this amount of gain must be at least generated to get the sustained oscillation or getting light output from the laser cavity. So based upon this formula we can have a numerical. So we have the active cavity with losses, this one, that means this is the transmission loss is there, alpha bar is given. Then we have the reflectivity as 30%, so it is 30 by 100, that is 0.3. So reflectivity of both the mirrors will be R1 equal to R2 equal to R will be 0.3. So length of the cavity is 600 micrometer, so L equal to 600 micrometer. So using these parameters from the previous slide, we have the formula for the threshold gain as this one. So putting the value of this alpha bar as 30, length of the cavity 600 micrometer, and reflectivity of the mirror as 0.3. So we can calculate as 50 per centimeter. So the minimum gain is 50 per centimeter is required for achieving the sustained oscillation by the laser cavity, or this is the minimum threshold gain required from the laser cavity. So that's all for this lecture. Thank you everyone. Jai Hind.